Hello everyone, welcome back to my channel. This is your academic coach Yuhyun. This would be my third video in how to cram AP Physics 1 in 1 hour series. Today I'm going to go over Unit 3, circular motion and gravitation. Here are the subtopics that I'm going to cover today in my video. First off, I'm going to start from the definition of circular motion, and then I'm going to compare centripetal force, centrifugal force, and net force. Then I'm going to jump into centripetal acceleration and its formula and tangential velocity and how these two are related to each other. Then it's going to be period and frequency. Then I'm going to cover the typical types of problems that you will see in AP Physics 1 related to circular motion, which are horizontal circular motion problems and vertical circular motion problems. Next, I'm going to get into Newton's law of gravitation, even though a lot of people believe that Newton is the most famous for three laws of motion, but Newton's contribution to physics actually relies on Newton's law of gravitation. And then I'm going to compare gravitational force and electric force, even though we don't have to actually learn electric force, but we need to know the similarity and difference between the formulas of these two. And then the last but not least, I'm going to go over gravitational field on different planets. Especially when it comes to moons. We're going to use the formula that you learned in Newton's law of gravitation to do some calculation and compare those values to gravity on Earth. Let's get started. So I'm going to start from the definition of circular motion. I always emphasize to my students that definition or the concepts are the most basic thing you have to know when it comes to physics because you actually need to understand. Otherwise, there's no way for you to solve any types of physics problems without understanding. Well, just by the name suggests, circular motion is really simple. It means an object is moving along this circular path. So we know that when it comes to one-dimensional motion, it literally means an object is moving in a straight line from left to the right, or it means an object is going up and down, or along a ramp, an object is going up or down. This is what we mean by one-dimensional motion. When it comes to two-dimensional motion, it literally means that an object is moving on a flat surface. Well, the direction doesn't have to be specified. So this is a two-dimensional motion. This is a two-dimensional motion. And the projectile motion, is also a two-dimensional motion. So circular motion is also one type of two-dimensional motion. When it comes to circular motion, a lot of times we refer to it as uniform circular motion. What does that mean? What does the term uniform refer to? So uniform here just means that an object is doing circular motion at constant speed. Now here comes the question. Why didn't I use the term constant velocity? Why do I have to specify that this is constant speed instead? Well, we know that the difference between the speed and velocity is that velocity is a vector quantity, which means it comes with both magnitude and direction. So according to Newton's first law of motion, when there's no external force applied on an object is doing a constant velocity motion. And what I mean by that is an object is moving in a specific direction at the constant speed, which means this object will move in a straight line infinitely along that direction. So there is no way for a circular motion to be constant velocity motion. That's not possible. So if it's moving at a constant rate, we call it as uniform circular motion. So this is the key concept when it comes to circular motion. Next, then let me explain the difference between centripetal force, net force, and centrifugal force. First off, in physics, when it comes to circular motion, the force that results in such a motion is called centripetal force, and we refer to it as Fc. Well, it seems like we've never learned this type of force in Unit 2 when we were learning dynamics. Well, it's not like gravitational force or friction force or tension force or elastic force. Then what is this exactly? Centripetal force is not a type of force like tension force or gravitational force. Centripetal force is just another name for net force. Then why do I have to learn this new term called centripetal? We call it bicentripetal force because when it comes to circular motion, any object that goes through circular motion experiences a net force that points toward the center of the circular path. So because of that, we give it another name, we give it a nickname called centripetal force. So let's say an object is right here going through the clockwise circular motion. Then its net force is pointing toward the center. Well, now let's say this object has moved all the way down here around the bottom of the circular path. Then this time its net force would be pointing to the circular path, pointing to the center again. So the direction of the net force of an object going through circular motion is changing all the time. So at this point, the net force would be pointing toward this direction. So now you see that at every single point along the circular path, the direction of the net force is consistently changing, but it's always pointing to the center. That's why we call it bicentripetal force. Okay, then what about centrifugal force? A lot of you have heard of the term centrifugal force, especially when you were dealing with centrifuge in biology class. Well, we know that centrifuge is an apparatus that you use to separate the liquids mixed together depending on their density, the difference in the density. So it's used a lot to separate the plasma from your blood sample. But there is no such thing as centrifugal force in physics, actually. So centrifugal force actually is a type of misconception in physics. Okay, then now let me explain this. Let's say let's say I am holding a string, and then an object is attached at the other end of the string. I'm just gonna swing this string. So this object goes through the circular motion in air. What happens here is this object is going through circular motion because it is attached to the string and because I am holding the string. So I am actually pulling the string all the time. So this object goes through the tension force, which points to the center, and this tension force is actually the net force contributes to the net force of this object, assuming that this object has a very, very small mass. So I'm just going to assume that its gravitational force is very, very small, almost negligible. So what is the so-called centrifugal force? Well, actually, when you're doing the swimming experiments, you will feel that someone is like pulling your hands or pulling your hand outward. Well, I feel that force on my hand, and a lot of people call this as the centrifugal force. But actually, this is a misconception. Why? Okay, so on this end, the tension force is applied on an object by the string. Then on the other hand, by Newton's third law of motion, which is action reaction, the string must also apply the tension force in the opposite direction, but with the same magnitude. So basically, this is the action and reaction between my hand and then this object. My hand is pulling the object, then this object is also pulling my hand. So there is no such thing as centrifugal force, and that's just a reaction force to the tension force that I'm applying on this object through the string. Well, what's really interesting here is what happens if I cut the string at a certain point. So let's say this object is going through the circular motion, and then I'm just gonna and then I'm just gonna cut this string at a certain point. Then what happens is this object will just fly upward instead of flying away from the circular path. A lot of people might think that, oh, this object will just fly away from the circular path due to the non-existent centrifugal force. That's not true. Okay, again, according to Newton's first law of motion, when there's no net force applied on an object, what does an object do? This object will merely keep moving in that specific direction at the same velocity, right? So again, assuming that this object experiences very, very little of the gravitational force, then this object will merely just move in that direction. Because right at the moment of cutting off the string, this object was moving straight up, vertically upward. So it's going to keep moving upward. So centrifugal force is merely what people feel on their body when they're holding an object and doing a circular motion on that object. So this is a misconception. And there's no force, no such force as centrifugal force in physics. Then let's jump onto centripetal acceleration and tangential velocity, and then the formula for all of these, including centripetal force. Well, so centripetal force has a formula of Fc is equal to mv squared over r. Here, m obviously refers to the mass of the object, and v refers to the velocity of the object, and r refers to the radius of the circular path. We also know that centripetal force is just another name for net force, and net force has a formula of F net is equal to ma, and we know that this is exactly the same as mv squared over r. This means that acceleration in acceleration in circular motion is equal to v squared over r, and this is exactly what we call by centripetal acceleration, and we refer to it as AC. Again, AC does not mean that this is a very special type of acceleration. No, it's not. It literally just refers to acceleration of an object under circular motion. That's it. It just refers to acceleration in a very specific circumstance, which is circular motion. Okay, then we know that since net force and acceleration are always pointing in the same direction, so this centripetal acceleration must also be pointing to the center all the time. For any of the object that's going through the circular motion, its centripetal acceleration is also pointing to the center. I'm just going to refer it as AC. When it comes to circular motion, an object's velocity is always along the tangent line on a circle at the specific point. So let's say this object is moving in the clockwise direction along the circular path. Then at this specific point, the direction of that direction of this object, the direction of the velocity of this object points along the tangent line. Remember what is a tangent line? So tangent line literally means a linear line is attaching the circle at one specific point. So these means it's not tangent line because there are two intersections, and this is not a tangent line because there's no intersection, and this is a tangent line, this is another tangent line, this is another tangent line. There is only one intersection of this line and the circle. We call those lines tangent lines. And the velocity of an object going through circular motion always points along that tangent line. This is v. Okay, then at the next moment, let's say after a short period of time, this object has moved to this point. Okay, then I'm going to draw another tangent line right here, and I'm going to call it v2. Well, so in this short period amount of time called called delta t, the object's velocity has changed from v1 to v2. Remember that we're assuming a uniform circular motion, so magnitude of v1 and v2 would be the same. Well, remember, acceleration has a formula of change in the velocity over time, which was v2 minus v1 divided by time t. Then v2 minus v1 would be this tiny vector. I'm going to refer to it as delta v. Now imagine that when it comes to acceleration and velocity, well, even though we don't require AP Physics 1 students to know the calculus, but we know that this instantaneous acceleration is calculated when the delta t approaches 0, which means when we take a very, very, very small increment of time. Well, now assume that this delta t is super small as 0.00001 seconds. Then what's going to happen is v1 and v2 are almost the same. v1 and v2, they separate by like very, very, very like minimum amount of angle, let's say 0.01 degree. So in result, the delta v would be almost perpendicular to v1 and v2 because v1 and v2 are almost parallel to each other. So the difference between them would be just perpendicular to those directions. So that's how we come to the conclusion that the delta v is in the perpendicular direction of the v1, and thus acceleration is in the perpendicular direction of v1. And then next, I'm going to briefly go over period and frequency. You will also see these terms later in in unit 6 when it comes to simple harmonic motion. So when it comes to any of the cyclic motion, which means it's a repetitive motion, then you will see the term period and frequency. So period in such motion literally means the amount of time it takes for one full revolution or one full cycle. So for a circular motion, it literally means I'm going to pick a specific point, and then when an object starts from this point, and then when it goes through one full revolution and come back to the point again, then the amount of time it takes for that path means period. And it's measured in seconds, obviously, which is the SI unit for physics. Okay, then what about frequency? So frequency is just a reciprocal of period. So for period, we use the capital letter T to represent it, and for frequency, we use F to represent it. And F is equal to 1 over period, and it is measured in per second. So frequency literally means how many revolutions I am doing in 1 second. So for example, 5 per second means in 1 second, I am going through 5 cycles or 5 revolution. So that means in 1 second, I am doing 1, 2, 3, 4, 5 revolutions. Okay. So what would be the amount of time it takes for 1 revolution then? Well, I'm just going to take the reciprocal of that, well, which come out as 0.2 seconds. That means because in 1 second, I can do 5 revolution. So in 0.2 seconds, I can do 1 revolution, which is exactly the amount of time it takes for 1 full cycle. Okay, then is there any formula for period or frequency? Yes, for the period, we actually can use a very, very, very simple formula that everyone can just deduce. So given that the radius of the circle is r, then the circumference of a circle would be 2 pi r. Time it takes for traveling a certain distance would be equal to the amount of the distance traveled divided by the average speed. So here v does not refer to velocity, it just refers to the magnitude of the uniform circular motion's velocity, which is just a speed. Okay, then in this case, we can replace the c with 2 pi r, and it becomes 2 pi r divided by v. Well, sometimes v, the average speed, is not even given. Then how do I figure it out? Well, we know that from the previous formula that we learned. So centripetal acceleration, AC, is equal to mv squared over r. So given that I know the centripetal acceleration and mass and the radius, then the v squared would be equal to AC times r divided by mass. So the average speed of a circular motion would be equal to square root of ACR divided by mass. And then I'm just going to plug this in the formula of 2 pi r divided by v. So a lot of formulas are just interchangeable. Okay, next, I'm going to briefly go over the most important types of the circular motion problems that you will see in AP Physics 1. First, I'm going to go over the horizontal circular motion on a string. Well, so let's say I am holding a string. The person is holding a string in his or her hand, and then on the other end of the string, an object, or let's say a block, is attached, and then I am just swinging this object. So the object is going through the circular motion in air. Well, this is the side view. And now I'm going to draw the top view again. Well, this would be the top view. Okay, and now I'm going to try to draw the free body diagram. Well, we know that this object has a mass, and then it must experiences gravitational force that points vertically downward. I'm going to refer to it as mg. At the same time, this object also is also attached to a string, and then I am pulling a string using my hand. So my hand is also applying a tension force along the string. I'm going to use Ft to represent it. Well, there's no other forces, assuming that it's just moving or swinging in air, and there's no surface supporting it, and there's no wall right against it. Its net force must be pointing in the direction diagonally. It must be pointing in the direction that points slightly down instead of horizontally to the center. Yes. So there's something wrong about it, wrong about my diagram. This means that actually the net force of these two, the vector sum of these two forces, mg and ft, should point horizontally. That means I must be holding the string a little bit higher than where the object is. And then the string would be in this slanted direction. By then, the tension force would be pointing slightly upward, and in results, the tension force and gravitational force add up to a net force that points in the horizontal direction, that points horizontally to the center of the motion. Okay, so from a top view, this would be how the centripetal force is pointing at. How the centripetal force is pointing. So by analyzing the situation of the tension force and gravitational force and their vector sum, it is pretty obvious that when it comes to swinging an object in air horizontally, it's impossible for the string to be perfectly horizontal. It must be slightly pointing downward. Next, I'm going to discuss the horizontal circular motion situation of an object on a disk. So let's say here is a disk, and then an object is placed on the outer edge, close to the outer edge of a disk. And this disk is doing a circular motion in the clockwise direction. And again, this is the side view. Well, then this object with mass m must be experiencing gravitational force which points down, mg, and then because it has the disk supporting it from the bottom, supporting it upward from the bottom, so it experiences a normal force that points upward. Well, there must be some force missing. Why? Because these two forces, which is up and down, must be canceled out because it's not doing any vertical motion up and down. Well, but then where's the net force? Where's the centripetal force? Since this object along the disk is doing a circular motion, it must be experiencing some kind of force that's pulling it to the center. Well, then the only possible force that it might be experiencing would be static friction force, assuming that this object does not slip off from the surface, from the top surface of the disk. Static friction force is the only force that's actually holding this object. Well, imagine this is the top view. If this disk is super smooth, it has a super smooth surface, and there's no static friction force applied on this object, then what happens is once the disk starts moving, and because this block already has a velocity of v, without any friction force, the net force that experiences is equal to 0, and then it will just keep moving in that specific direction, and then it will falls off the surface of the disk. Well, but that's not the case. We observe that this block is moving along the disk on top of the disk. It means there must be a static friction force that's holding this block, preventing it from slipping off the disk surface. Now I'm going to go over the vertical circular motion on a string. When it comes to vertical circular motion, it's different from horizontal circular motion. How so? When it comes to horizontal circular motion, well, on a top view, it's pretty obvious that it is symmetric from 360 degree. So no matter which position you take on a circular path of a horizontal circular motion, it will be exactly the same. But when it comes to vertical circular motion, the situation is different, and that is because in a vertical circular motion, usually gravitational force is directly involved in the vector sum of usually gravitational force is involved, and the centripetal force changes its direction as the object changes along the path. Well, now let's take a look. Now assume that a string is attached to a bucket, and then I am swinging the bucket along a vertical circle. Then at the very bottom of the circular path, a tension force is applied on the bucket, and this tension force points up, obviously because the string is at the top of the bucket. I'm going to label that as T up. I'm going to label that as T bottom, which means it's the tension force applied on a bucket at the very bottom. And this bucket also experiences a gravitational force mg that points down. Well, we know that the centripetal force, aka the net force of an object, will be pointing toward the center of the object. So at the very bottom, the centripetal force is pointing up. So that would be T bottom, the tension force, minus mg. This means the tension force at the bottom of a circular path would be equal to centripetal force Fc plus mg, or mv squared over r plus mg. This means T bottom, so at the bottom of the circular path, the tension force must be greater than the gravitational force. It's greater. Well, what about the bucket is at the very top? When the bucket is at the very top and it's upside down and the string is still attached to it, then the tension force must be pointing downward. Well, the tension force is pointing downward, and then I'm going to label it as T up, which means the tension force applied on the bucket when it's at the very top. I'm going to label as T top, which means it's the tension force applied on a bucket when the bucket is at the very top of the circular path. At the same time, the gravitational force of the bucket also points down. Well, we know that, again, centripetal force points to the center, which is downward here. So Fc would be equal to T top plus mg. So it's pretty obvious that T top would be equal to Fc minus mg. So the T top might be a very small value, might be larger than mg, might be smaller than mg. Well, we only know that at least it needs to be something greater than or equal to 0. So sometimes in the questions it might ask you that, oh, what would be the minimum possible tension force that could be applied on an object when it's at the very top that would be equal to 0. So it will be assuming that the string is not applying any force on the bucket when it's at the very top. Then that means that centripetal force would be equal to the gravitational force. Okay, now I have explained all types. Okay, and then let me explain one more types of the vertical circular motion. So this one is actually pretty similar to vertical circular motion on a string. The only difference is this time instead of string, we're gonna discuss the case where an object or where a person reside in a roller coaster. I usually call it the roller coaster question. So now assume that I am sitting in a roller coaster. I'm riding a roller coaster. Okay, that at the very bottom, well, this time we don't have the string, that at the very bottom, this person experiences a gravitational force that points down and then the normal force that points up. This normal force is applied by the seat of the roller coaster on the person. Again, at the bottom, the centripetal force points up, so it results in normal force minus mg. So normal force would be equal to Fc plus mg. Again, normal force this time is greater than mg. What about at the very top? Well, at the very top, the roller coaster and the person are upside down. And this time, mg points down, while normal force also points down. And the centripetal force points downward because the center of the circular path is in the middle. So Fc would be equal to normal force plus mg. So normal force again is equal to Fc minus mg. And again, the smallest possible normal force would be equal to 0. There is no way that this normal force is negative number. If it's negative, it just doesn't make sense. So it's greater than or equal to 0. So now I've explained all types of circular motion problem that might be tested on AP Physics 1 question. Question number 1. We have figure 1, figure 2, and figure 3. A car travels with a tangential speed v1 around the curve of radius r and turn to the left as shown by the rear view of the car. So this is the, okay, so this is the rear view of the car, and then assume that it goes straight, it goes forward, and then it's making a left turn. So it's moving along the circular path by turning to the left consistently. Okay, and a force diagram of the force exerted on the car with speed of 5 meters per second as it turns is shown in figure 2. Okay, so in figure 2, this car is doing a circular motion at 5 meters per second, and this is how the force diagram looks. Well, a force diagram of the forces exerted on the car with a speed v as it turns around the same curve of the same radius. Okay, the same radius, same curve is shown in figure 3. The speed v of the car in figure 3 is most nearly, okay, so now let's try to compare the free body diagram of figure 2 and figure 3. In both figures, normal force and gravitational forces are canceled out. So there is no vertical force components in results. So I only need to pay attention to the horizontal force on this free body diagram. In figure 2, okay, so obviously centripetal force is equal to this amount of friction force, and centripetal force, according to the formula, is mv squared over r. Well, in figure 3, now I observe that the centripetal force has became 9 times greater. So it's 9 times of the ff. Well, And because it's still the same car, so mass is the same, and it's still the same radius, so the radius is still the r. The only difference would be v, because it has been increased by 9 times, and then in this formula, velocity is in the form of square. Is square, that means the velocity must have been increased by 3 times. So 5 meters multiplied by 5 meters per second multiplied by 3, that would be 15 meters per second. And next, a satellite orbits Earth in a circular path at a constant tangential speed. So this is uniform circular. So this is uniform circular motion. Which of the following correctly represent the direction of the net force F net, acceleration A, and tangential velocity vt of the satellite at instant shown in the figure? So the satellite is right here around the bottom. So the satellite is right here around the bottom part of the circular path. And since this object is going through a circular motion in the counterclockwise direction, so its velocity must be pointing to the right along the tangent line at this specific point. So this represents VT. So I can immediately cross on number C because it does not have the correct direction for the velocity. Okay, then what about acceleration? We know that acceleration, especially the centripetal acceleration, always points toward the center of the circular path. So AC must be pointing upward at this point. So I know that it's going to be A for sure. And net force, okay, since net force is exactly the same as centripetal force, so it has the same direction as the centripetal acceleration. So net force and acceleration should both point toward the center. So A is the answer. And next, let's try to go over this question. A horizontal circular track for running has 4 lanes. Various runners of different masses use the track. In each case, the center of mass of a runner follows a circular path around the track in one of the lanes. Consider a runner in lane 1 with speed v1 and a runner in lane 4 with a speed v4. v1 in V4, where the ratio of the speed of V4 to V1 is equal to 2. The radius of lane 4 is B times the radius of the lane 1. Radius of lane 4 is equal to B times radius of the lane 1. And both runners have the same mass. Okay, so I'm just going to assume that both have the mass M. Which of the following claims is correct about the net force F1 and F4 exerted on the runner in lanes 1 and 4 respectively? Okay, again, so assuming that this person is doing a circular motion along the track, then this person experiences a centripetal force towards the center, and then by the formula, Fc is equal to mv squared over r. Okay, then for lane 1, its force F1 would be m times v1 squared over r1, and then F4 would be equal to m times v4 squared over r4. Okay, and because because V4 is 2 times of V1, that means V4 squared is 4 times of V1 squared. And R4 is B times of R1. So in result, F4 would be 4 over B times of F1. Okay, so F4 is equal to 4 over B times F1, so B is the right answer. Next, a student swings a ball of mass M on the end of a string in a vertical circle of radius r, as shown in the top figure above. Also shown is a diagram of representing all of the forces exerted on the ball at the bottom of the circle, where its speed is v0. What is the magnitude of the acceleration of the ball at the bottom of the circle? Okay, so we know that the radius is r, the mass of the ball is m, and then it has the speed of v0. Well, actually, no matter how the force diagram looks, we know that its centripetal acceleration is always equal to mv squared over r. The problem is here, Okay, so here we need to use the F tension and F gravity to represent the acceleration. Well, at the very bottom, which is right here, we know that the centripetal force must be pointing toward the center, which is upward. So it means the upward force must be greater than the downward force. So Fc is equal to F of tension minus F of gravity. And then since this is equal to m times a, so acceleration would be equal to Ft minus Fg divided by mass m. So the answer would be D. A ball of mass m is swung in a vertical circle with a constant tangential speed. Figure 1 shows the forces exerted on the ball at the top of the circle, and figure 2 shows the forces exerted on the ball at the bottom of the circle. Which of the following is an expression for the centripetal acceleration of the ball in terms of m, t1, and t2, and fundamental constants? Okay, so figure 1 represents the ball at the top. Well, we know that at the top, the center would be at the downward. So centripetal force also points down. So here, Fc is equal to Fg plus T1. So Ma is equal to Fg plus T1. Acceleration A is equal to Fg plus T1 divided by M, which is equal to G plus T1 divided by M. Well, I don't think any of the options in out of A, B, C, D refer to that. Okay, now let's take a look at figure 2. For figure 2, this is at the bottom. Okay, and at the bottom, the center must be at the top. So centripetal force points up, and that would be equal to T2 minus Fg. And again, this is equal to ma. So acceleration is equal to T2 minus Fg over m, or T2 over m minus g. And we know that these two values should be exactly the same. So I'm going to set up an equation of T2 over m minus g is equal to g plus T1 over m. Then I'm going to move g to the right hand side and move everything else to the left hand side. Then I get T2 over m minus T1 over m is equal to 2g. So T2 over T1 over m is equal to 2g. Okay. Then now what I can do is I can try to represent G in terms of T1, T2, and M. So G would be equal to T2 minus T1 divided by 2M. And then I'm going to plug that in this formula. Then I get G, then I get T2 minus T1 over 2M plus T1 over M, which is T2 minus T1 plus 2 twice of T1 over 2m. So this is equal to T2 plus T1 over 2m. So the answer would be D. Okay, a student must test the maximum force exerted on an object attached to a spring before the string breaks. The student ties the object of mass m0 to one end of the string and then uses the other end of the string to spin the object at a constant speed so that the object travels in a horizontal circular path, as seen in figure 1. Figure 2 shows the horizontal force exerted on the object at time t0. In a second trial, what should a student do to increase the tension in the string while keeping all quantities constant? Okay, so according to this diagram, I can try to draw the free body diagram, and the object experiences a gravitational force that points downward, and then it also experiences a tension force that points to the person. Well, we know that right here, the tension force is equal to centripetal force, which is m, V squared over R. Well, so when we were trying to increase the tension force, we need to increase any one of these. So either we need to increase the mass or we need to increase the speed of the rotation, speed of the circular motion, or we need to decrease the radius. So we can either A, increase the mass, yes, that works, or B, increase the length of the string. Well, if R goes up, then actually centripetal force will go down, so not B. C, decrease the time required for one rotation. Well, if the time requires for one rotation decreases, that actually means the average speed would be increasing. Well, with a larger speed, then centripetal force is greater. So C is also correct. And D, decrease the height of M0 above the floor. So the height of the mass above the floor is irrelevant, so not D. So the answer would be A and D. Now let me go over the second part of the unit 3, which is gravitation. So I'm gonna start from the Newton's law of gravitation. Newton's law of gravitation is one of the most important laws that Newton has discovered in the history of the physics. And its importance in physics actually overweighs the importance of the three laws of motion. So according to Newton's law of gravitation, any two objects that has the mass will apply a gravitational force on each other. So even between you and me, there is a gravitational force going on. So I am actually attracting you, any of my students, and then you guys are also attracting me. The problem is, then why are we not feeling that attraction between each other? So when I'm sitting right next to my friend, why am I not attracted to my friend as if she or he is physically pulling me? That's because the mass of like a regular human being is just way too small. It's way too small to the point that gravitational force that's created between two human beings are just too small, and it's almost negligible, so we barely feel it. Well, then what are some examples of gravitational force that we actually feel? That would be when you are when you are close to a planet, something that has a huge amount of mass, such as the Earth, such as the moon. Well, when you're standing right on the Earth, you feel the gravitational force. How do I feel it? Well, if you throw something, that the stuff that any object will immediately drops downward. That's due to that gravitational force, the Earth pulling any object downward, vertically downward. And this is because the Earth has such a huge mass. So the gravitational force is not negligible anymore. So Fg, the gravitational force would be equal to G multiplied by mass 1 multiplied by mass 2 divided by r squared. Okay, so here mass 1 and mass 2 refers to the mass of any two objects that are attracting each other. So mass 1 and mass 2. And here r does not refer to the radius. Here r refers to the distance between the center of these two objects. Again, r does not refer to this distance. No, r refers to how far the centers of two objects are apart. This is what we mean by the radius r. Okay, and then what about the capital letter G? So the capital letter G refers to the gravitational constant, and it has the value of 6.67 times 10 to the power of negative 11. Well, this is not something you have to memorize because obviously this constant will be given in the equation sheet during the test. So again, when it comes to gravitational force, the most important part is any two objects with mass attract each other. So it's not just Earth pulling me down. I am actually also pulling the Earth up. Earth is also feeling the gravitational force applied by me. But why is Earth not moving? It's because this amount of gravitational force is way too small when it comes to Earth. Also, on the other side of the Earth, there are so many people, there are so many buildings, so many animals out there. They are also pulling the Earth in the opposite direction, while I'm pulling the Earth in this direction. So that's why all of these gravitational forces kind of cancel out, and Earth just remains constant. And what's really important here is since any two objects attract each other, so this is actually a pair of action reaction. So let's say here I am pulling the earth. Well, then the earth is pulling me down. So this is the gravitational force applied by earth on me. Then at the same time, I am also pulling the earth upward. So this is a gravitational force applied by me on earth. And these two are a pair of action reaction. And remember, according to the properties of the action reaction, these two forces have the same magnitude but opposite direction. Okay, so let's say here we have the moon and the earth. Then moon is applying a gravitational force on earth, which points to the center of the moon away from the center of the earth. We call it FG earth. Okay, then earth is also pulling the moon toward its own direction. Let's call it FGM. Then these two forces are of the same magnitude but opposite direction, and they share exactly the same formula. For their magnitude, it would be equal to G, the gravitational constant multiplied by mass of the moon multiplied by mass of the earth divided by the distance between them, divided by the distance squared between them. The distance divided by the distance between them squared. Okay, then what is so important about this formula? Well, actually, this formula have exactly the same form as the electric force, even though we're not going to actually learn electric force in AP Physics 1. So for gravitational force Fg, it has the formula of a constant multiplied by the product of the product of the mass of two objects divided by the distance separated by them squared. Well, for electric force, it follows exactly the same formula. Fe is equal to K, also a constant, multiplied by Q1, Q2. So Q refers to amount of the charge. So and divided by the r squared. Again, divided by the distance separated between objects squared. So now you can tell that both of them have exactly the same form. A constant multiplied by the product of the two objects, either the mass or either the mass or the charge, and divided by the radius, the distance squared. Okay, so this is pretty important because it means that when you are getting away from an object, the further you are away from an object, then the smaller the gravitational force or electric force becomes. And greater the mass or the charge of an object, then greater these forces become. Okay, the last but not least, let's try to go over gravitational field. Okay, so gravitational field, a lot of times we know that we just use G to represent it, which refers to gravity or gravitational acceleration. Okay, first off, gravity and gravitational acceleration are interchangeable. They mean the same thing. A lot of people think that gravity referred to Fg or the weight, but that's not true. That's one of the misconceptions you need to avoid. Gravity literally means gravitational acceleration, G, 9.8 meters per second squared on the surface of the Earth. Well, then what is gravitational field? Think of the term field. Field means a space, like the space where the children just played a soccer game with each other, or the field where you work at. Well, so here in physics, field means a three-dimensional space. And then once an object enters this space, then it will experiences some type of force Well, sometimes it's electric force, sometimes it's gravitational force, sometimes it's a magnetic force. Well, when it comes to gravitational field, it means that, let's say, around the Earth or around the moon, around any of the planet, once you enter that field, or once you enter this three-dimensional space, then the object will always experiences a gravitational force, no matter where you are in this field. If you're inside a field, you always experiences the gravitational force. That's what I mean by field. Okay, then here, gravitational field literally means how strongly the Earth or other planets will pull this object at. Well, um, we do not use the force to represent it because every single object has different mass, and depending on the mass, the amount of force will vary. So here, when it comes to gravitational field, we use the gravitational acceleration to refer to how strong it is, aka we use G to represent it. Well, we learned that G is simply just 9.8 meters per second squared on Earth, but that's not completely correct. That's only on the top surface. That's only when it's right at the surface of the Earth. What does that mean? It means if you are at the in air up there, not on the surface of the Earth, then the gravity or the gravitational field you experience is not going to be 9.8 meters per second squared. Well, how do I calculate that? We're going to use Newton's law of gravitation. According to Newton's law of gravitation, Fg is equal to gravitational constant multiplied by mass of this object, mass of this unknown object, multiplied by mass of the Earth, assuming that this object is right at the surface of the Earth. And okay, then this time the distance between the object would be exactly the same as the radius of the Earth. Okay. Then what I do is I am trying to separate m, the mass of the object, from all the other variables. Then it becomes m multiplied by gravitational constant multiplied by mass of the Earth divided by the radius of the Earth squared. Well, this formula looks pretty familiar to us. Remember that gravitational force formula is Fg is equal to mg. So these two parts are actually exactly the same. So what does that mean? It means the value of the 9.8 that we got on Earth is actually calculated by G multiplied by mass of the Earth divided by radius of the Earth squared, which means if I ever change to another height, let's say I am right now like 0.5 times of the Earth's radius above the surface of the Earth, then now I will have to exchange R to 1.R. Then this time the gravitational field I experience would be less than 9.8 meters per second squared. Okay, so for example, let's say this is at the top of the Earth and this is the radius of the Earth, and some object is at twice of the radius of the Earth away from the center of the Earth. And I'm just going to call this object M1, and here we have M2. Okay, then what is the gravitational field experienced by object M1? Okay, when it comes to object M1, the gravitational field experience would be equal to G times mass of the Earth divided by the radius squared, but here radius does not refer to radius of the Earth. It refers to the distance between the object and center of the mass, which is twice of the radius of the Earth. Well, so that will be 1/4 of GME divided by RE squared. We know that this is approximately 9.8. So at that height, this object M1 experiences only 1/4 of the regular gravitational field that we experience in real life, which is approximately 2.5 meters per second squared. Now let's try to go over the rest of the questions related to gravitation. At one point in their individual orbits, three planets X, Y, and Z are along the same horizontal line. The gravitational force on planet X from planet Z is F0. Okay, so planet X is experiencing some kind of gravitational force by planet Z. Okay, that must be to the right because planet Z is on the right-hand side of planet X, and that's F0. And we know that F0 would be equal to G multiplied by mass of the planet X, which is M0, multiplied by mass of the planet Z, which is 9 times M0, divided by the distance they're separated, squared, which is 3 times R squared. So that's GM squared over R squared. And the distance from the center of the mass of each planet to an adjacent planet is given in terms of R, and their receptive masses are given in terms of M. What is the net force on planet Y, and what reasoning supports the claim? Okay, for planet Y, it experiences gravitational force to both sides. One is applied by the planet Z to the right, the other one is applied by planet X to the left. So for Fxy, that would be equal to G times M times 4M divided by R squared. Okay, that would be 4 times of the gm squared over r squared. That will be 4 times of F. Okay, what about the gravitational force experienced by planet Y due to planet Z? Fyz. Okay, then Fyz would be equal to G times 4M multiplied by 9M divided by 2R squared. Well, that would be equal to 9 times gm squared over r squared, which is 9 times of F. Okay, so to the right, it's pulling in 9F. To the left, it's pulling at 4F. So in total, planet Y experiences a net force of 5F. So the answer would be C. The next question. Planet X has a mass of m and a radius of r. Planet Y has a mass of 3m and a radius of 3r. Identical satellite orbits both planets at a distance r above their surface. The planets are separated by such a large distance that the gravitational force between them are negligible. Okay, how does the magnitude of the gravitational force Fy exerted by planet Y on its satellite compared to the gravitational force Fx exerted by planet X? Okay, so gravitational force of Fy is Fy is gravitational force experienced by the satellite around planet Y. According to Newton's law of gravitation, the magnitude would be G times mass of the satellite, let's say m, multiplied by mass of the planet Y divided by the distance between them, which is 4r here. So I'm going to take 4r squared. That would be equal to 3 over 16 times gmm over r squared. On the other hand, Fx refers to the gravitational force experienced by satellite due to planet X. And that's again g multiplied by mass of the satellite multiplied by mass of the planet X divided by the distance separated, which is 2r squared. So in total, that's 1/4 gmm over r squared. So by comparing the coefficients of Fx and Fy, it's obvious that Fy is equal to 3/4 multiplied by Fx. So the answer would be C. That's the whole review for Unit 3 of AP Physics 1, Circular Motion and Gravitation. If you find this video helpful, please subscribe to my channel and like this video, and also refer my channel to your friends and your classmates so everyone can have access to this free resources. Also, I really appreciate it if you could leave a Google review for me. Okay, I will come back with more videos.